Thanks for being there. We're almost at the end of the session, so it's probably has been a long way. So I'm going to talk about what we're doing in user space networking with RDMA. So it's not really about RDMA per se. You will see that in the course of the talk. My name is Benoit Gann. I'm working at Cisco, and I'm working on VPP. So for those who missed the excellent talk about Quick from my colleagues, a few words about VPP. VPP is user space software networking platform, and it strives to be very, very fast and have a lot of features like tunneling, routing, switching, all those kind of stuff, and even layer 4 like TCP, UDP, and now Quick. But at the very bottom of our stack, we need to receive and transmit packets, and we need to do that efficiently. And from time to time, we ask ourselves the question: okay, do we need to write our own network driver to do that? And sometimes we have to. So first, why do we do user space networking? Mostly because of performance, but also because it allows us to update more easily network functions in the field. If you have some of your networking functions that you need to update, you don't necessarily want your whole host to be down because you need to reboot to start a new kernel. So this is the features that user space networking brings us. And then the next question is, okay, why do you need to write your own network driver? Especially as now, we have the DPDK, which have a lot of drivers already available, and we do use DPDK a lot in VPP. We rely on it for a lot of drivers, but sometimes for specific drivers, we want to go a little bit further in terms of getting better performance and ease of use. And in that case, we need to go to develop our own network driver. And this is an example here where we did a native development. It was for the Intel XL710, so 40 gig Intel NICs, where by developing our own native drivers, we gain about 25% performance boost on some workloads like IPv4 forwarding with 2 million routes. So that's something which is important for us. And one of the main reasons of that is because when you're using an external driver, you have, like DPDK, for example, you might have some translation happening between metadata. This is actually something that even the DPDK has, for example, with XDP, that they presented in an earlier talk. So when you get a packet from another driver, you usually need to convert the bits describing your packet, such as the length of the packet, is the checksum good, this kind of stuff. In VPP, we have our own representation. In DPDK, they have their own representation. In XDP, you have another one. So you need to translate between that, and that costs some performance. That being said, it's not always an easy decision because first, usually when you do user space networking and with your own user space network drivers, you're losing integration with the kernel. And that's a pity because you're losing, your favorite tools like ATH tool and blah blah blah, and it makes things harder to deploy, harder to monitor, etc. So that's one of the problems. Another thing is what we really care in VPP, for example, in our case, is we want to receive and transmit packet efficiently. We don't care about initializing the device, configuring it, making it work, but we have to. And unfortunately, it happens that most of the time, it's the most complex part of the work. When you write the drivers, there is a lot of codes which goes, and a lot of data sheet reading, which goes into, okay, how should I initialize it to make it work? And finally, something that we should not forget is, well, hardware is hard, and I will share with you some story later on about that. But that's basically our problem statement, let's say. So, RDMA. RDMA stands for Remote Direct Memory Access. It was designed originally for message passing and data transfer, especially for the HPC or storage applications. So it's a very efficient way to move data around in a network. And it has evolved to support Ethernet transport. So now we have RDMA protocols which runs on Ethernet and IP, such as IWARP and RoCE. And key properties of RDMA is, so you have some hardware offloads, it's kernel bypass, meaning that you get the data directly from the NIC without having to go through the kernel and sometimes have data copy, etc. So it's also zero copy, and it's usually very high performance. So it's looked like a good thing to use for networking, especially for user space networking. And on the right side of the slide, I tried to picture a very simplified way of how the RDMA stack looks like. So on the top, you have the RDMA NIC, the hardware in blue. In the middle, you have the kernel, which basically does all the configurations and control. And at the bottom, you have the user space. So you have a library in user space, which is called lib-ib verbs, and which is used to talk to the kernel, but also to the hardware to move data around. And at the bottom, you have the application. In our case, it's VPP, but it can be anything. The nice thing is with RDMA, the data move directly from the hardware to the user space software. So there is no data touching in the kernel at all. That said, we are not that interested in RDMA itself in VPP, at least for now. We're more interested in Ethernet packets. And it happens that RDMA has been extended for Ethernet support somehow. And they introduce a new kind of queues that you can use to send and receive Ethernet packets, which is called queue pair type row packets. And the nice thing about it is it relies on packet steering to move back to, let's say, to steer packets between different queues. So that allows the kernel network device to stay with its own set of queues for receiving and transmitting packets, while your applications get a different set of queues, and your application can also receive and transmit packets. And the hardware will actually select which queues it needs to send packets to based on flow you program. So that allows you to have your user space applications having a direct access to the network hardware while retaining your kernel net device. So your net device does not disappear suddenly because you start your application. And as the packet steering is based on what you want to program there, you can implement things like similar to MAC VLAN or IP VLAN. So you can say, oh, my application is interested in all the packets with this specific destination MAC, for example. If you or my application is interested by all the packets with this specific IP, and you can go even further up the stack if you will. It depends on the capabilities of the hardware, basically. So nice model, and this nice model is actually quite easy to use, at least if you use lib-ib verb. So here is a simplified example, but the full example you can have a look at a simple but fully working example on GitHub here. The full example is like 200 lines of code, so it's not very complex, right? And it's depending on your hardware, your mileage might vary, but typically for me, it allows me to send like 20 million packets per second with one CPU. So it's it's not bad for a simple, stupid test. So the way it works is you just get a handle on the device you're interested in, and this is all user space, right, with some help from the kernel here. Then you initialize your queues. So RDMA has a concept of queue pairs. So you basically get queues to push the packets and queues to get the results of what you do. And the same is true for receiving packets. You get queues to push your descriptors to tell the NIC where it must put the packets you're interested in, and completion queues, again, to get notified when new packets are coming. And then you just push your work queue elements, which are like IOVs, IO vectors, and you do that in a loop. And that's about it. So that's pretty cool. You can go a little bit deeper with direct verbs. So again, it's an extension in IB verbs, which allows you you do the same thing as previously, but you just get the direct access to the hardware rings. So instead of going through the mediation of the libIB verb to get your packets, you go directly to the DMA rings, which is really great because in that case, you don't have any metadata translation anymore. You just get the raw packets given to you by the NIC. So that's pretty cool. An example for us, what we first developed an IB version for the driver. And yeah, it gives us around 20 million packets per second for a layer 2 cross connect. So a layer 2 cross connect is just you move packet around between two ports, but you check that the Ethernet headers, etc., are well formed. So you're still touching the header of the packet, but you don't do much. So it gives us around 20 million packets per second. Next step is direct verbs. So going for the hardware rings. And yeah, while doing that, I actually I was trying to debug my drivers. I saw that the NIC could give me some hardware traces. I tried to enable that, and I almost broke it. So that's why you need to be careful about when you're doing very low-level development with hardware. And yes, the next step we will like to add are support for things like checksum offloads and TSO. So in conclusion, what I would like to say is, as a user space networking developer, we really like this model. We like the fact that we don't need to write any code to initialize a NIC. That's great. We like the fact that we are not stealing the NIC from the kernel. That's really cool too. And of course, we really like the fact that it gives us great performance. But this has some limitation. First, it's RDMA, so it's restricted to RDMA capable NICs. And more precisely right now, it's something that Mellanox came up with, and thanks to them for that great technology. It works really well, but well, there's only Mellanox for now. So if other vendors could also support that, we will be very happy about it. And the final thing is, it's a little bit outside of my domain knowledge, but I'm wondering, okay, could we apply the same kind of features with other mechanisms? For example, maybe VFIO MDev could allow us to get, we don't touch the NIC for initialization because we don't care about that, but we get direct access to the rings. Maybe AFXDP also could help us in there. So right now, my understanding of AFXDP is you still have some metadata conversions between what the kernel gets and what it gives you. So that means that you get some decreased performance because of that. But maybe we could use that also as a foundation to have something similar. So I don't know. That's just food for thought, and that's about it. So, and I don't know if there is any question. Yeah.
Why do you use the RDMA hardware to send packets over the RDMA, or to use the RDMA hardware to send the packet like the networking over just the RDMA hardware, that you are not adding the RDMA tunnels?
Okay. So the question is, do we use this to send a packet over the RDMA stack, so like IWARP or ROCKY, or do we use that to send raw Ethernet, standard Ethernet packets? So this is actually the second. We don't use at all RDMA protocols per se. We're just using the RDMA infrastructure to send and receive raw Ethernet. There is no IWARP, no ROCKY there. It's just using the infrastructure which is already there, but instead just sending Ethernet packets.
Yeah. Why did you try to write your own implementation of sorry, why did you try to use direct verify yourself and did not use DPDK implementation?
Okay.
It already exists and already debugged and
Right. Yes. Well, the reason is mostly because of this. So the
yeah, but performance in DPDK, I assume that it's already have maximum available performance.
Sure, if you can fit in the DPDK metadata format and etc. The issue we have with VPP is it predates DPDK by like 10 years. And so we have our own buffer metadata format, and we can change that easily. I mean, it will be basically a complete rewrite of the whole code base, which is not doable. And so it means that no matter what we do, we need to pay the tax of converting RTE-MBUF format to our own metadata format. And so you have an example here for the Intel XL710. The DPDK driver for the Intel XL710, I'm sure, has the greatest performance you can get, right? But when we integrate it into VPP, because of this metadata translation and blah, 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 we're losing performance on the table. So that's one of the points. The other point is the ease of use, which we found that DPDK can be quite picky about what it needs to run. Like, it really wants huge pages and this kind of stuff, which is not always easy to get in, containerized environment, etc. And so that's another thing we try to overcome with that.
Sorry, we need to kind of continue to switch to the next speaker.
Thank you.